So, geotrig, lesson 34. The first thing we're going to talk about, guys, is summation notation. Summation notation is just a different way of adding a list of numbers. We use the Greek letter sigma, that big E-looking thing, because it's the Greek letter S for sum. And the summation, the sigma, has a couple different parts to it that we're going to talk about. Well, first off, it starts off with the variable of summation. The variable that we are going to replace always starts off with, on here, equaling a number. That number that it equals is the lowest number, or the first number I plug in. The number on top is the number we stop at. So, down here, the variable is a y, and every y is going to be changed out with a 1, and then it's going to go to 2, 3, 4. And it goes by integers, whole numbers, nice things. And that's what I'm going to plug in to what we have here called the typical element, or the element. The element in this case is a y squared. So the y, because I know it's a y, because there, is going to replace with a 1. So it's 1 squared. And then I'm going to go and put a 2 in. So it becomes 2 squared. And then 3 squared, and then 4 squared. And what do I do with each one of those events? Add them. It's the sum. So you add them all. Now, on the bottom there, I do have it that it says it takes integer values above and below sigma, and the range from there, it's all integers between those, and then you add them up. So, what does that example here look like when we actually plug those numbers in? So, it looks like the top example here, where, like I talked about, I'm going to plug a 1 in for y, then a 2 in, 3 in, 4 in. And then I'm squaring it because the element says y squared. So it's 1 squared plus 2 squared plus 3 squared plus 4 squared. If you evaluate that all the way out, you end up with 30. So the answer of the sigma of y squared from 1 to 4, or the summation from 1 to 4 of y squared, is 30. Now, let's look at the one underneath it. The summation variable is an I this time. That's going to start at 2 and go to 5. Now, the variable that's going to be replaced with numbers is an I. But our element has an I and a K in it. The K is just K. K is just going along for the ride. So, I just replace the I with a 2, then a 3, then a 4, and a 5, and add them up. Notice that I did not touch K. K is left alone there. And so, what's 2 plus 3 plus 4 plus 5? 14. So you end up with 14. Okay. We starting to get this? The idea that we're just plugging in numbers for the variable it tells us, and in this case it's I. We're going to get a little bit tougher problems here, which really isn't that much tougher. On the top one here now, it's the summation of I from 1 to 5 of 3. From 1 to 5 of 3. Where's the I, because that's the variable I got to replace, in that problem? I don't see an I here. Well, guess what? I still have to have it. I still have to do this. I still have to take it from 1 to 5. The problem is, if I'm not plugging the value in, it ends up being, when I equals 1, the answer is 3. It's a constant. Just like y equals 3. No matter what x value I put in, the answer is always 3. So, wait a minute. When I put 2 in, it's 3. I put 3 in, it's 3. Put 4 in, and put 5 in.
That's supposed to be the tougher problems?
It's tough because all of a sudden you're like, hey, where's that variable? what do I do with my numbers? It's adding 3 5 times, which ends up being 15. Now the next one has something we can plug in. What does it end up being? It's the summation from 1 to 4 of 2x. So 2 times 1 plus 2 times 2 plus 2 times 4. Now the toughest thing about this, or not this problem, this one's pretty straightforward, but it starts getting tougher is when you start to add a whole bunch of fractions together. Because to add fractions, you need to have common denominators. 2 plus 4 plus 6 plus 8. 4 and 6 make a 2 and 8 make a, so the answer is 20. 3rd grade math on that one. Quite literally, my daughter does that, or actually 1st grade. Grouping to 10, right? The whole idea, we can add 10s very quickly. So use that to your advantage. Now we're getting a little bit tougher. This is kind of one of your tougher type problems. Now, the summation of j from 0 to 3, when you have your element is 2 to the j power over j plus 1. You just plug in j equals 0, 1, 2, 3 for j. And add them all up. Very easy. So 2 to the 0 over 0 plus 1 plus 2 to the first over 1 plus 1. Yeah? Next one. 2 to the second over 2 plus 1. And 2 to the 3 plus 1. I think those can be reduced. So 2 to the first power is 1 over 1 plus 2 over 2. Hey, that's kind of nice. And then it becomes 4 over 3. And 8 over 4. And now, what? 1 divided by 1, 2 divided by 2, 8 divided by 4. Those are fairly easy. That's 1 plus something plus 2, right?
Yeah.
And, wait, that's 4/3 in the middle there. That means I have to have a common denominator. Well, first of all, 1 plus 1 plus 2 is... So it's 4 plus 4/3. I'm going to let you guys handle that, but the common denominator here would be 3, and so you multiply the 4, which is 4 over 1, by 3 over 3, so you can gather it together. Make sense? Yeah. So these are really not that bad. Does it take a little time when you get those fractional ones? Yeah, it's okay. No, it would not be your answer. Again, you have to put it together. I'll let you guys do that. Next one, from 4 to 6 of 1 over y. So this problem has 1 over 4 plus 1 over plus 1 over 6. Get a common denominator. What is the common denominator of this one? I'll let you guys do this one on your own as well. It's not 10 because 4 does not go into 10 or 6. It's not 20 because 6 does not go into 20. It's not 40. 6 doesn't go into 40. It can be 120. But there is a smaller one. 60. Why? Because the 4 is a 2 and a 2. Yes? Think going back to our LCD days. Break it down. 2 and 2. 6 is 2 and 3. Guess what? The 6 doesn't get to bring its 2. So it's 4 times 5, which is 20, times the 3 from the 6, which is 60. Leave the 2 at home. So therefore it's 60. That's how I do it. Make it a little easier. You could just multiply all the denominators together to get 120. Just at the end you have to reduce. So, not so bad, right? Now, let's talk about these. Guys, if I remember correctly, those who had me in Algebra 1, we may have done a line of best fit as a project. I think mini marshmallows or something.
Oh my god, I won that.
And so, the idea, guys, same thing. Line of best fit, guys, is where we try to take an experiment and we gather data about it. We plot that data on a graph and say, hey, what's the typical trend going on here? And can I predict the future? That's what we use these for. You use them in science, you use them in real life. Projecting your profits or your losses for something. You take a sample of something and enlarge it or push it out in the real world in the future. And so it's just a model, a relationship between dependent and independent variables, and we use it on scatter plots. Now, the biggest things that I want to highlight are those things right here. It has to fit your trend, number one. This is the positive correlation, negative correlation, and no correlation. If there's no correlation, then you can't draw a line of best fit. If there's a positive correlation, it looks like a line's going through there with a positive slope. If it's a negative correlation, it has a negative slope attribute. It falls down. Okay? Now, also, huge thing that you need to realize. You're going to draw your line with half the data points above, half the data points below. This line does not have to even touch any of your data points. I'm going to show you a couple graphs that have that option. Some of them touch it, some of them don't, and it's okay. Computer-drawn lines of best fit, if you guys ever use Excel or Desmos, it can do it for you, and they're more exact than we will ever be. And I think a lot of our elementary school teachers or 8th grade, 7th grade math teachers have done us a little bit of disfavor with the last point here, because some of them just said, hey, if you just connect the first point and the last point, and then connect those with the straight line, you'll have the line of best fit. No, that is not necessarily true. Could it be true? Yeah, it could be, but more than likely it's not going to be. And number two, it does not have to go through zero. Those are some things that I see consistently when I do these types of problems. And so, you're going to plot your data, you're going to draw that line of best fit, and your line of best fit is going to be different than your neighbor's. Not everybody has the same line of best fit. Which then, you have to pick points on your line. Just because your friend picks some points doesn't mean you pick those same points. He has a different line. You find the slope between those lines. Wait, what is slope again? M equals that's the slope formula. So you can take your 2 points and find this slope. And you're going to put it into point slope form, which is y minus times x minus x1. Using those two things, you'll be able to create a line which is a prediction of the future. Okay? You can use it to predict the future or the current trend. Okay? That is your equation. Of course, you solve it for slope-intercept form because it's y equals mx plus b. Are we ready? Let's take a look at a couple different graphs here. We're going to actually find the line of best fit on one of them. The first one here, I have the temperature in degrees Celsius and amount of money earned for something. Since they're yellow dots, let's talk about lemonade. The hotter it is, the more lemonade we're going to sell. Okay? This has a positive correlation. Would you guys agree?
Yeah.
It's got their line is following a positive slope. They're kind of grouped together, which basically says the hotter the temperature, the more money I make selling lemonade. Yes?
True.
That's how you can read graphs. Now, look at this one. What we're doing is we're seeing that half my data is above, half my data is below. And I think we could say that, oops, wrong one. That this point is on the line. I think that's pretty obvious. It looks like it's going straight through the middle. That last point is on the line. But can I say the same thing for this one? Maybe not entirely. So therefore, I would not want to use that point. I maybe want to use this point. So like 16 and a half, 325. This one over here would be like 25, 625. Are you guys seeing those values there? And again, look at the scale. I might be off. Someone else might say, oh, that's not 625, 625. That's 25, 610. That means their equation will be even slightly different than my equation, even if I use the same exact points in that area. Okay? So, looking at where these lines go, I have seen, and this is no joke, lines that best fit that way. Half above, half below, right? But that doesn't follow the trend. It has to follow the trend. The blue line is the line of best fit. Okay? So be very careful on that. This one is a little bit harder to read. It says the French mark and the German mark. I'm guessing the values or something on those lines. But we can see that as the French mark goes up, the German mark goes up. I don't know what these are. I just pulled these offline. But look at this line of best fit. Does it touch any of my points? No. It doesn't have to. So, this is what I do. I go here and I find nice points. And I think right there is a nice point. It's on my line. And it looks like it's 40, 40. Would you guys agree with that? And then I go find another one. This one right here looks nice. What is that one? 50, 50. Hey, was anybody actually, just by knowing those numbers, what's the slope? What's the slope going to be? Not 10 over 10, but 10 over 10 is 1. It's going up and over the exact same amount, right? So the slope of this one would be 1. Now, here's the thing. If I start doing that and I start backwalking that slope, as I start to get closer to here, that means it should actually be on this point. So these points are not perfect, but it's good enough to make my prediction. Okay? So what this is, this equation will allow me to say, if I put in a value for the French mark, then we'll know what the German mark will be, give or take. Because obviously they're not perfectly on that line. Give us a rough estimate. Any questions to that? The one that I want to do together is this one, pulled offline. I guess it says, more wine consumed, the heart disease deaths goes down.
So that's like promoting wine?
I guess, I don't know, I didn't realize what it was before I pulled it off. But, here's the thing. Can you guys say, what kind of trend is this? It's a negative correlation, right? That means as something goes up, the death rates go down. Now, where would a line of best fit be here? Well, see, if I start drawing some lines in, I'm going to change colors so that we can see it better. Is that okay?
No.
Which way do you think it should go if I have to change it? I think I need to take in consideration maybe a little bit more of this stuff, because these are going to pull the line up a little bit more. But we have a large stack of points over here. So I'm going to change colors so we can leave that one on there at least. I don't want to go to red. We got red on there. Let's use a black line. It doesn't have to be perfect, because a bigger, what we call outliers, those points like this one right out here, he's affecting the graph in that direction a little bit more than the others, because he's further away. And so, I don't know, let's take a look and try to do something like that. Let's just do that. So again, this is kind of up to everyone's interpretation, but I definitely would not want to see a line that, there it is. That's not good. And so, Now, what I need to do is find some points on my line. Find some nice points. I don't even want to necessarily use the points that are there. So, if I'm looking at that black line, I hit 250 at, no, that's not even 0. Because you notice the spacing doesn't go to 0. It's a half. So, okay. Can we take that as 1/2, comma 250?
Yep.
I don't really know if that's a necessarily nice number, but we could use it. Where else can we see? Can I use 4 150? Is that a nicer one?
That's like
Oops. That point right there? It's about 4 150. We'll just use it. So now, I have 2 points, so I'm going to find the slope. So that would equal 150 minus 250 over 4 minus a half, right? What's 150 minus 250? Negative 100 over 3.5. Well, we don't like 3.5. Would that be 7 halves?
yeah.
What happens when I divide by a fraction? Flip and multiply, right? So that means the 2 gets multiplied to the top. So negative 200 over 7. That is not a nice slope. But it's a negative. It should be negative, right? And now, I pick a point. Which point do I probably want to choose? You want to use the one with the half? I'd rather not use the one with the half. I'm trying to avoid fractions, but we created one. And x minus 4. And then you just distribute and gather like terms, right? We've done that many times. We've done it in this class. You've done it in the last 2 years. Okay? So I'm going to let you guys finish that off, but distribute the negative 200 over 7 and add 150 to it, getting a common denominator to put it together. Any questions? And the last thing of the lesson is decomposing functions. Back in lesson 24, guys, we put together functions. We did composition. We tried to make them take 2 separate functions and take out a variable and place it in there. That created a new function. Today, we're going to go the other way. We're going to take a look at one function and say, hey, what can I see in there that I can say is nestled inside of another one? And so there's some of these problems have many, many, many solutions, like our first example, and then the second example, there's only one solution. Now remember when we did composition, they were both equations most of the time based off of x, right? F of x, g of x. And so what we did was we took out an x and placed in the value of g of x. Notice the notation of f composite g, the little open circle, f composite g of x. It's saying that the composition is equal to the square root of x squared plus 1. So what it's asking us is, what is f of x and what was g of x? What were they, or what could they have been, before I decided to put them together? Remember, which one's the inside function? Which one's inside? F composite g. One of them's inside.
Inside what?
Inside the other. F composite g of x. F of x was your outside function. G of x was your inside function. I'm placing g of x inside of f of x. And when I did that, the way we did this was I removed x, the variable x, and replaced it with g of x. We got to go the other way. We have to say, what was g of x? If I state what g of x is, then I could find out what f of x is. What looks like it's inside of something else on that problem? Looking at the square root of x squared plus 1. What looks like it's inside of something else? X squared plus 1. So if I named g of x is x squared plus 1, what's the outside thing? What's the thing we didn't use? This square root. But in the original process, that would have been f of x. So I can't just say it's just a square root. It would have been the square root of x. Because what happened, remember, when I put those together, I take x out and I put g of x in. I'm switching. I was switching the x for the g of x. What goes inside of the other? That's not the only option for this problem. There's another slight variation I could take. I can say g of x is an x squared plus 1. What happens if I just say it's x squared? What's the outside function then? Still has a square root, because I need that. It's x plus 1. Because remember, just because I take the x squared out, that was g of x. It went in for an x on f of x. So these ones can have multiple answers. That's just 2 of them. That problem, and I think that would be it. So you don't have to have both. You just have one or the other. The bottom one, there is only one solution. The original problem is f composite g of x is 1 over x squared plus 1. They're telling you g of x is the x squared plus 1. So that means f of x only has one choice, and it will be the 1 over x. Because that's the only option. So I'm replacing that x with an x squared plus 1 of g of x. And we're done. Any questions? Homework is lesson 34, page 245, 5 through 13 and 17. Have a fantastic day.